Hey everybody, today is day 11 of Math 133, and today we're going to cover the Chapter 5 review, which starts on page 390 in your course pack. We're going to do more of the sample midterm. The sample midterm is different from the midterm. The sample midterm covers it's a worksheet and it covers all the same material that you'll find on the midterm, but you're going to turn it in before taking the midterm, and then the midterm is going to happen on the 26th. Uh, last time we talked, I talked about the midterm uh, in general. I also sent out an email with a document that gives you a lot more information about the midterm, about like the options, take it with me or take it at the testing center, right? So if you have questions on the midterm, feel free to ask. You can either ask me here, you can message me and remind, or send me an email. Okay. Um, okay, so today though, chapter 5 is about probability and starts on page 390 in your course pack. You don't need to click on the link in Canvas. There is a link. I don't know why they put it there, but if you click on, yeah, don't click on this link because this brings you to the data set or the all the worksheets for all the data sets for our worksheets. There isn't one for the chapter 5 review. Just go to page 390 and we'll start there, okay? All right. So just like our other worksheets, we'll go through it twice. We'll go through it once, give you some hints that'll help you with studying for it, and then we'll go back through and fill in all the rest. Um, a game at a fair consists of tossing a three. A game at a fair consists of tossing a fair three-sided dice. It's weird. Uh, yeah. Okay. Fair at a fair. Um, Three-sided die, one, two, three. It's a weird die. And then spinning a fair wheel. Can we say the word fair any more times? With three equal colors, red, yellow, or green. Okay. You are going to play the game once, construct a tree diagram to show all possible outcomes for this experiment, and also list the sample space. So a tree diagram, here you are at the start. The first thing you do is you roll the dice, okay? And there are three possible results for that. You could roll a one, roll a two, you could roll a three, okay? After you roll, whether you get a one, two, or three, okay, you then spin the spinner, and there are three possible results for that. And it doesn't matter whether you roll a one, a two, or a three, there's still three results, right? You could get red, yellow, or green, red, yellow, or green, red, yellow, or green, okay? This is our tree diagram, okay? This helps us when we are looking at probability where there's multiple steps, like if I roll the dice twice, or if I draw two cards from a deck, or, you know, two independent things happening, okay? Um, to list out the sample space, though, the sample space is different from the tree diagram. The sample space is all possibilities, okay, for both, okay, for the whole game, okay. This game that we're playing, you have to do two things, okay. You have to roll the dice and spin the spinner. So there's not three possibilities, okay. There's more than that. You could roll a one and get red, and that would be written like this, okay. You could roll a one and get a yellow, or a one and a green. Okay. That's three of the possibilities, but you could also have rolled a two and gotten a red, or two and a yellow, and two and a green, right? So there's actually three times three. There are nine possible results. Okay. Three green. Okay. And those right here, those are the nine results. I've listed all nine of them. Okay. Now, if we had a six-sided die, we would have six times three, would have 18, which is, not an outrageous sample size, not an outrageous sample size. It would take a while to write them out, okay? So I'm not going to make you do like something big like that. Even if you just have, so if you have a six-sided die and you roll it twice, and you then 6 times 6 is 36. There's 36 possible outcomes. Uh, it gets big pretty quickly. Rolling three dice uh, has 216 possible outcomes in its sample space. So it blows up pretty quick. So anyway, most of the sample spaces we'll have you list are pretty small. We're going to skip that one. All right, I want to point out question C because it's weird. So the events spinning red and tossing an odd number are disjoint, not disjoint, independent, dependent. Um, I didn't write this. These should be two separate questions, okay? Um, okay, first of all, disjoint means that they cannot happen at the same time. Okay. You're playing this game and you spin a red or you toss an odd number. If those two cannot possibly happen at the same time, we call that disjoint. Other classes may call it mutually exclusive. Okay. It's the same thing. Um, Not disjoint means they can. Okay. Can happen same time, right? Same game. I guess you can't play it happen at the same time because you have to roll the dice first and then you spin. You understand what I mean? I don't mean same time as in like the same moment. I mean that during the same result, the same sample space. Okay. Um, so can you spin a red and also at the same result, at the same time, get an odd number? Sure, you can. One red means I rolled a one and I spun a red, or three red. Okay. There's two possible ways that you can spin a red and get an odd. Okay. So in this case, is this disjoint or not disjoint? It is not disjoint. Okay. Now, I've already answered the question, but I haven't even talked about independent dependent. Okay. Independent and dependent are a different concept. Okay. And this should have been written as two separate questions. I apologize. Okay. So, independent means that the results do not affect each other or interfere with each other, do not affect each other. Okay. Dependent is the opposite. Dependent means one result that changes the other. Okay. Mhm. Um, for this particular case, um, if I roll a dice, does that change what's going to happen with the spinner? And the answer is no. If you roll the dice, you might get a one, you might get a two, you might get a three, but it doesn't matter what you get. When you spin the spinner, you're going to get a red, a green, or a yellow, and those probabilities aren't going to affect each other. In this case, these are independent. Okay. Um, an example of a dependent situation, uh, we'll look at in a second, but um, dependent would be like um, if let's say I rolled two dice and I needed the dice to add up to six. Okay. If I roll the first die and I get a one, that's going to change what I need to get if when I roll the second one, right? So that might be a bad example, but we'll talk more about independent and dependent. Now, it says here circle one. If you circle one of these, I will accept it. okay, for part C. We will see these kind of questions on the sample midterm and some of the other worksheets, the cumulative review. You won't see any of these on the midterm because I did write the midterm. You'll see them split up separately if you'll see something on the midterm, okay? So anyway, I don't like this question because there's actually two answers. I apologize for that. Um, okay, question D. Uh, events tossing less than a two and tossing at least a one. Are those disjoint, not disjoint, independent, dependent? Um, Rachel says not disjoint. So if you can those happen at the same time? Uh, can you roll less than a two? A less than a two is a one, right? So I need a one in this case. So a one or tossing at least a one means one is the lowest, so you need a one or more. Well, one or more is anything, any roll at all. So can you roll a one and also roll any number? Yes, you can. Those could happen at the same time. Um, yeah. And then again, it says circle one. If you've answered one, we can move on. Okay. Uh, if you really want to know if these are independent or dependent, uh, technically these are dependent. Yeah, that's going to just be confusing. We're not going to go into that. Okay. We'll talk more about independent and dependent as we go. We'll see more of that on the next page. Okay. Right. Um, the probability. So probability, all these probabilities, probability of this, probability of this, probability of this. Probability is the number of wanted outcomes divided by the total. Okay. So in this case, our total is 9. We have 9 possible results. And you're just going to say, all right, that's my denominator. In the numerator, how many uh, do we want? Okay. So for F, compute the probability of getting a number bigger than 2. So, well, there's only one number bigger than 2. It's 3. So there's one, two, 3 possible outcomes. So this would be 3 over 9. Okay. Now, it says give fraction, so you don't have to change this to a decimal. Uh, 3 over 9 can be written as 1/3. Okay. Um, so am I going to require you to simplify the fraction? Okay. No, if you write 3 over 9, I will accept that. Okay. Um, so we've seen in some of the other exercises that we've done, it'll say like give 3 decimal places or give 1 decimal place. Um, and you may have seen cases where you gave me the wrong number of decimal places and I gave you the right answer. Okay. I've said before, uh, I'm not nitpicking your answer. I'm grading your understanding. So if you write 3 over 9, then I'm like, okay, you know what you're doing. You know that calculating probability, you check, which of these outcomes do I want? Divide by the total number of outcomes. You know what you're doing. Okay. This reducing, this is not something we covered in this class. This is something, covered back in, you know, middle high school fraction class, right? So, um, anyway, would I love it if you simplify? Yeah, I mean, I always love additional math. So, okay, if you had written it as a decimal, I probably would have still accepted. Okay. All right, so we'll skip some of those. All right, the probabilities above are classical, empirical, and subjective. So classical is theory, okay? Um, empirical means you're looking at some kind of experiment or, actual data, okay? And subjective is made up. Now, that doesn't mean it's useless. Okay. So, all right. So, first of all, let's answer the question for question I. These up here above, are these classical, empirical, or subjective? Um, what do you guys think? Aldena's got it. Classical, yes. It's theory because we didn't actually play the game. We came up to this fair and they described the game to us and we sat here thinking about, okay, what's the sample space here? We listed out all these possibilities. Did we actually get all these possibilities? No. This is just all the possibilities listed out. When you play the game, you're going to play the game one time. You're only going to get one of these. Okay. Um, so it's not empirical because we didn't actually play. We didn't actually do it, right? Um, experiment. Um, that's hopefully pretty obvious. You actually have data that you collected, okay? Whether it's observational data or experimental data. So I shouldn't just put experiment. I should probably put observational. But anyway, it's from the real world, okay? Not that this isn't from the real world, but like we didn't actually play it. Now, if we had played this game 5 times and wrote out the 5 results we got, that would be empirical, okay? Next one is subjective, which is made up. And that's not to say that it's useless, okay? So made up would be something like if I said, you know, my friend asked me, like, are you coming to the party tomorrow? And I was like, I don't know. I'm 50-50 on whether I'm coming or staying home. Okay. Is there actually a 50% chance that I'm coming and a 50% chance that I'm not? No. I didn't actually do any math. I just, made that up, made that number up. Okay. But that doesn't mean that's useless. That number still gives my friend information that, oh, he might come, he might not, you know, maybe I'll make sure that we have enough food if he does come, but I'm not going to, depend on, I'm not going to, bank on that he's coming. Okay. I tell my wife, sometimes like she'll ask, like, did you do this or this? And I'm like, I'm 90% sure I did it, but I'll have to go look because I have to double check. So anyway, yeah, so I don't know if we'll see any subjective, but I always enjoy subjective probabilities. All right. Next page, page 391. Which of the following numbers cannot be the probability of an event? So Rachel says the negative. I agree with you. There is more than one. There are three of them here. So probability of an event is always between 0 and 1. Okay. So 103.9%, that is also not possible. Okay. Um, and then the last one, 4 over 2, 4 divided by 2 is 2. That is bigger than 1, so it is that one. Yep, you guys got them. No problem, right? So uh, in this class, we're going to be dealing with probabilities and proportions uh, and percents, and those are all interchangeable. Okay. Probabilities, proportions, and percents are always going to be between 0 and 1. It can be 0, it can be 1, okay, but it can't go above 1, it can't go below 0. Okay. It's kind of like the correlation coefficient, except the correlation coefficient can go below 1. It can be in the negatives, right? All right. All right, question for following table shows the probability distribution of blood types and rhesus factors for a random sample of people living in Quebec. Okay. Um, all right. So blood type, is that qualitative, quantitative discrete, or quantitative continuous? What do you guys think? Blood type. Yeah, Rachel's got it. If I asked you, what's your blood type? You might say O or you might say O positive, I guess. You might say A negative, right? But those are not numbers. Those are letters. Those are categories. Those are qualitative. Okay. All right. We have a whole bunch of these disjoint, not disjoint, independent, dependent craziness, right? All right. So let's talk more about these. For a single person, all right, so you go up to one person, uh, A and B blood types are disjoint, not disjoint, independent, dependent. So can someone be both A and B at the same time? Okay. I'm not talking about AB. AB is a different type. I don't know why they didn't call it C, right? It should be A and B and C. This is a different type of blood. Uh, can someone be both A and B at the same time? They cannot. So these are disjoint. Okay. Disjoint means they cannot happen at the same time. All right. Now, if they are disjoint, they are automatically dependent. Okay. Why does that matter? Because if if I go up to this person and they say that they are A blood type, that automatically means they cannot be B. So he said dependent means one result changes the other. If this person is A, it automatically changes their answer to the B question. Okay. So do you need to circle the dependent? No, you do not. You'll need to circle one of these, but I want you to at least understand what both of these different topics are. Okay. For a single person, again, A and plus blood types are disjoint or not disjoint. Can someone be A plus? A plus, that sounds like it's the best blood type, A plus. Uh, Yeah, well, Donna's got it. These are not disjoint. They can happen at the same time. There were 481 people in Quebec that were A plus. I think O plus is probably better, right? I don't know. Did they list them in some order? Probably not. They're not in alphabetical order, so why is O first? I don't know. I have heard that O is like right, the universal donor or the universal receiver. Anyway, uh, so if they're disjoint, they're automatically dependent. If they're not disjoint, it could be either one. So if I go up to someone and they say that they are type A, does that change whether they're going to be plus or minus? It does. You'll notice that uh, there were 481 positive A plus A's, right? A pluses, but only 96 negatives. So if this person is A, it changes their answer to positive or negative because they're much more likely to be positive. So these are actually dependent, okay? For two related people, so uh, mother and son, or two siblings, uh, if the first person says that they are O positive, um, the second one says they're O positive, can those events happen at the same time? Are those disjoint or not disjoint? What do you guys think? Yep, these are not disjoint again. Good. And well, Donna's already ahead of me. Nice. Um, so if the mom says they're O positive and you know the son says they're O positive, yeah, those can both happen, right? It is possible for two different people to have the same blood type. Now, if the mom says she's O positive, is that going to change the probability that the son is O positive? Yes, it does, because we know that for related people, you're more likely to have the same blood type. So these are dependent. Okay. All right. Lastly, for two random unrelated people, so me and my friend, uh, A for the first person and A for the second person. Can we both be A? Even though we're not related, we're not cousins or anything like that. Can we both be A? Disjoint or not disjoint? We can both be A, absolutely. So that those can happen at the same time. So that is not disjoint. Now, if I say that I'm A does that increase the probability that my friend is also A? It does not, right? These are independent, okay? Um, because I mean, unless we became friends over like me donating blood to him, I don't think that's what happened. Uh, if I'm not related to them, then me being A like doesn't change the chance that they're A. Okay. Hopefully that makes sense. Okay. If it doesn't, that's okay. You only need to circle one of these four. Okay. So as long as you understand that it's not disjoint, then you're good. Okay. All right. We're going to continue talking about blood type on page 392, so I need to not throw that away. Um, choosing one person at random, find the probability that the person is Rh negative. So again, probability is you're gonna write out the number of wanted outcomes divided by the total number of outcomes. Okay. So I'm gonna skip that one. Uh, the word or. We need to be careful with the word or in statistics class. Okay. It is different from the word or in English. Okay. Um, so you know, if if I went out to dinner with my daughter and I was like, all right, what do you want to eat? You can have pizza or ice cream. No, sorry, I wouldn't say pizza or ice cream. We're gonna have ice cream for dinner. Let's say pizza or cheeseburgers. You can have pizza or cheeseburgers. In English, the word or is understood to mean this or that, not both. Okay. If I ask my daughter, what do you want for dinner? Do you want pizza or cheeseburgers? She can't say, oh, I want both. We're going to go to two restaurants and get, food for both, right? Um, it's understood that when I say or, it's actually an exclusive or, okay? In statistics class, though, when we say or, it is possible that both happen at the same time. We just talked about not disjoint events. And when you're calculating the number of outcomes or probability, you need to pay attention to whether they are disjoint or not. So at the bottom, so for question H, we'll look at the bottom of page 254, and there's rules for probability. The uh, addition rule number one for disjoint events is if you have E or F, okay, you just add them together. Now that's if they are disjoint. So pizza or cheeseburgers would be an example of disjoint events. Can she have both of those? No, I'm not going to buy her both pizza and cheeseburgers. She's not going to eat all of it. Um, on the other hand, if it's not disjoint, then when you are looking at an or situation, you still add the two together, but then you have to subtract the overlap. Okay. And the reason why is because if you don't, you'll double count those. Okay. Um, anyway, so we will make sure we're paying attention as we're looking at or. So there's that. This is at the bottom of page 254. Uh, not A or B is also on the bottom of page 254. The word and is a little bit easier to deal with than the or situation. Uh, and it doesn't even say it. And you just look where they overlap. So in this case, type AB and RH positive. Well, here's positive. Here's AB. Where do those, where does this row hit this column? Right here, 48. Okay. Here's another or, so we need to be careful with that. Okay. Choosing three unrelated people, find the probability that all three have O positive. So there's a multiplication rule for independent events. So as long as they're independent, you just do the probability of this one, probability of this one, probability of this one. These three people are unrelated. We've already identified that when you're unrelated, they're independent, so you're just going to multiply them together. So all of this stuff is the same, that same box at the bottom, page 254. Um, this one's tricky. Probability of at least one. So we should probably do that one. Probability of at least one. The probability of at least one event in n trials is this crazy thing, okay? Which you could also do it as this crazy thing, okay? So let's actually look at that one. Three unrelated people. Find the probability that at least one person is A negative, okay? So the probability of at least one A negative in three people is. All right. I'm going to write it out as the second one right here. 1 minus P naught E to the N. Okay. So it's still doesn't make any sense. So let's write it out. Let's see what it looks like. It's the probability of not A negative. And then you close two parentheses, and then you raise it to the number of people. So there's two parentheses here. Okay. All right. So there's that. That's still confusing, I think. So this right here, probability of not A negative. Okay. Well, let's come over here and calculate that. These are it's kind of like two problems in one. The probability of not A negative is 1 minus the probability that they are A negative. Okay. That's the complement rule here. Probability of not E is 1 minus the probability that it is E. Probability of one of not A negative is 1 minus the probability that it is A negative. All right, let's calculate that. 1 minus the probability that someone is A negative. What is the probability that someone is A negative? A negative is there, 96. That's the ones we want. I know that it's weird because the question is asking that, we want one person being A negative. Anyway, don't worry about that. Probability of one person being A negative is 96 over total. What's our total in this case? The total of the total is 1,363. That's the total. All right. Let's calculate that in our calculator. So someone want to do that in decimals for me? I don't have it open. I'll get it open here in a second. Somebody do this for me. 1 minus 96 over 1363. Don't need any parentheses around anything. It's 0 point something, right? Because all probabilities are between 0 and 1. And you know it's not 1, it's not 100%. So we can do it together. 1 minus 96 over 1363 is 0.92. How many decimal digits we got? Four decimals. So 9296. Now, this is not the answer. Okay. We're not done. These, when it says at least one, it's basically two problems in one. You have to do the probability that one person is not A negative, and that's this. There's a 92% chance that a single person is not negative. Okay. We take this and we plug it in here. Okay. So the probability that not A negative is 0.92 9296. So our equation is going to look like this. 1 minus 0. Oh, I need parentheses. 9296. Actually, I don't need parentheses at this point, but whatever. Okay, I'm running out of space. That's okay. 1 minus 0.9296. Now, how do we do to the power of 3? You hold the shift button and hit 6. There's a little up arrow, and then you can hit 3, and that'll make it cubed. Yep, Aldana's got it. Final answer is 0.196. We'll have to round that second 6 up. 7. 0.1967. That's our answer. If that was confusing, I understand. We'll do more of these. We have another cumulative review coming up, which is going to have some of these on it. And there's also one on the sample final exam. Okay. All right, let's move on. Which of the probabilities above are unusual? So on the front of our exam notes packet, um, we said that something is unusual, and there's 2 bullet points here. If the z-score is between 2 and -2, within outside of 2 standard deviations away from the mean. That's if you have a z-score. Every z-score, which are these on the x-axis here, every z-score has a corresponding probability, okay? So we say that, 95%, that's our usual data. Outside of that is 5%. So when we're talking about probabilities and percents and proportions, any value with a less than 5% probability are considered to be unusual. So you need to pay attention to whether you have a z-score or a probability. Are you comparing to 2 and -2, or are you comparing to 5%? Okay. In this case, we have probabilities. So we are looking for which probabilities are less than 5% or 0.05. Okay. So, all right. The probabilities above are these: classical, empirical, or subjective for the blood types. What do you think? These are empirical. Yep. This is real data from people that we sampled in Quebec. So this is actual data. It is empirical. Yep, you guys got it. All right. Page 393. This probability distribution shows the primary home heating fuel in New Mexico in 2023 by type, according to data from the U.S. Census. Probabilities of the different home heating fuel types must add up to what? So if you have a probability distribution, then the total, when I add all these up, is what? I don't need you to actually add them up. Yep, Nicole's got it. It's 1. If it's a probability distribution, then that means you've listed all possible results, and the total is 100%. Okay. Type of heating fuel is qualitative, quantitative discrete, or quantitative continuous. Qualitative. Rachel says qualitative. Agree, disagree, same answer, different answer. What do you think? Good. You guys got it. It is qualitative, because these are all words. Okay. If I asked you what your heating type was, it's words. Don't get thrown off by the fact that these probabilities are decimals and you're like, oh, well, it's continuous. Okay. Um, no, when we're talking about probability, we are almost always measuring qualitative numbers. Okay. Uh, that doesn't make any sense. Qualitative numbers, qualitatives are not numbers. Qualitative categories, and how many, what frequency of things fall into each of those, which are numbers. Yeah. All right. Anyway, for one household, the event's primary heating fuel is electricity, and primary heating fuel is wood. Are those disjoint, not disjoint, independent, dependent? Somebody give me a guess on one of these. Well, Dana says disjoint. Rachel agrees. Yeah. Uh, it is possible for a house to use electricity and wood for fuel, but your primary means the one you use the most, and you can't use both the most. Okay. Even if you use them exactly the same amount, you're only going to be counted once in one of these categories. So disjoint. If it's disjoint, it's automatically dependent. Okay, so if you said that your primary heating fuel is electricity, that automatically affects your answer to the following event. Primary heating fuel is wood. It automatically makes your answer no to that. Okay, so uh, for two random unrelated households, the event's primary heating fuel is electricity and primary heating fuel is wood. Um, are those disjoint or not? Those are not disjoint, right? If if I say electricity and my neighbor's wood, that's totally fine. Actually, it says unrelated, so I don't know. Neighbors probably not. It's not random then in that case. There we go. So, independent or dependent. So, if my answer is electricity, uh, I would argue that my neighbor would be dependent because it's more likely that we all use the same type on the block, but this is random unrelated households in New Mexico. So if, I'm living in Santa Fe and my answer is electricity and some other guy somewhere else uh in Albuquerque is saying wood, like are those independent or dependent? Those are independent. My answer doesn't affect his. All right. If you select a random household in New Mexico, what's the probability that the primary heating fuel is bottled gas or solar? Watch out for the word or. You need to, if it's or, then you might be able to just add them together, or you might have to subtract the overlap. Okay. If you select random household, it's not utility gas. We talked about that. Okay. Question H is another one of those at least ones. Okay. So this one is page 254, uh, um, rule 5, right? At least one household is wood. So to do that, it's basically two parts. You have to first calculate what's the probability of not wood. You plug that in here, 1 minus the number you get, and then you raise it to the power of how many houses you're looking at, in this case, 2. Okay. All right, that's all the hints I'm going to give for now. So I'm going to stop the recording.